Hello, this is Doug Halsbrell, your professor from statistics. We're covering our first set of notes for this semester. This is over sections 1.1 through 1.3. Just kind of getting into the idea of what statistics is, kind of working with data, different ways to collect data. So we're going to kind of cover an overview of statistics. Something to know about this set is that we do have a homework assignment over this set of notes. But we really aren't going to see a lot of this on the test because this section is mainly a lot of definitions. And I tend to test more over actually completing the calculations, doing the work. There's not going to be a lot of like definition type questions on the exam. So just a heads up, you don't really need to worry about having these super well memorized for an exam. But you will need to kind of know these definitions because they are going to come up throughout the semester. We'll see a lot of these words pop up as we go further in the course. So it's good to be familiar with these, good to understand these terms so that as we keep coming back to them throughout the course, you kind of have an idea of what's happening. So first off, statistics course, big question, what is statistics? Well, statistics by definition is a science of collecting, interpreting, and presenting data. That is statistics. So statistics is the study, the science of going out and collecting data, taking the data back and interpreting, understanding what it means, and then presenting it to people. These are all aspects of statistics. And what is data, though? Because that's a big part of that. Well, data is any collection of observations. So data is a collection of observations. So there's lots of different things you can collect observations about. You can collect observations about people's height, weight, age. You can collect it about the type of car they drive, where they live. It could be about animals, it could be people, it could be about buildings. So there's all kinds of things that can be data, but it's a collection of observations, something you noticed about a group of objects or people. Now, when you work in data collection and statistics, you have to be careful about whether you're working with populations or samples. These are two very important distinctions in statistics. Population you should think of as the entire group. This is everyone. So if I want to think about the population of the planet, that's every person on the planet. That's the population. A sample is just going to be a piece or a part of that. So if I'm thinking of the entire globe, the entire Earth as the population, then the population of the US would just be one sample. So population, again, population is the entire group. That's what you're thinking of when you think of population. So all of the subjects or objects that you're studying. If I'm looking at houses in South Dakota, that could be a population because it's all the houses in all of South Dakota. If I look at, the trees in a forest, the population might be the entire forest of trees. That'd be the whole thing. Versus a sample, again, a sample is not the entire population, it is just a portion of the population. So if I'm thinking of all the trees in South Dakota, again, a sample could just be the trees in one particular forest, just the Black Hills, not all of South Dakota. Or a sample could even be smaller. It could just be 16 trees that I've tracked over a year out of all the trees in South Dakota. So any smaller group, smaller portion of the entire population could be a sample. It's very important when you're trying to determine whether it's a population or a sample to think about the fact that population is everything. It's the whole group, and sample just a part. So this really depends on what the whole group is. If I'm thinking of entire trees of all of South Dakota as the population, then that's the population of all the trees in South Dakota. But in my difference heading, I might think of just all the trees in the Black Hills of South Dakota, just the Black Hills trees. That could be the population. So it really depends on the definition of the situation, what you're studying. So, when we measure populations, we measure censuses. So the census is when you collect data from the entire population. So when they do a census every 10 years, the US, they're trying to measure everything in the entire country. It's not really possible. There's always something you miss, but that's the idea. Census is a big deal because you're trying to collect data from the entire population. So census is when you measure the entire group, the entire population. When you do a sampling, the big difference with census versus sampling is just collecting data from a sample. So just part of the group. I'm not looking at everybody in the whole US. I might just be taking 10% of them and just measuring that. So it's just collecting data from a sample, not the whole thing. Okay, the data you collect from your population gives you stuff you can measure, and those measurements, if you measure for a whole population, are called parameters. So a parameter is a numerical measurement for the population. So when I tell you how many people are in the US, because I've actually gone out and counted all of them in a census, that's what you're supposed to do. Again, it's not really possible, but if you could count everybody in the entire country, you'd be collecting a parameter, which would be the numerical measurement, would be the count, how many people there are in the US. Or if you find out what percentage of people in the US have own a home, then that would be a parameter, because that percentage would be a numerical measurement. It's a measure of the percentage of people that own a home. Versus a statistic. So a statistic is when you take a numerical measurement of a sample. So that's the big thing. So all these again are sample values, and then over here all we have is population. So sample, a sample is a part of a population. We do sampling where we collect data about a sample, and then we measure statistics, which are measurements of the sample. So if I take a sample of 10% of the population of the U.S. and I find out in that sample that half of those people own a home, then that 50% of that half is a statistic because it's a measure of the sample, not a measure of the entire population, because I don't really know how many people in the whole country have homes just from that sample. But from that sample, I know that sample has 50% of those people own homes. So again, population is the whole thing, so that's everything. So population census parameter, this is dealing with the entire population. You want to measure the whole thing. These are usually really hard to do. It takes a lot of money, time, and effort to try and measure a population. So in a lot of cases, this isn't really possible. So most of the time, we actually spend our time collecting sample data. We'll go out and collect data about a sample using a sampling, and then from that, we'll calculate statistics. We'll use this usually to kind of make some kind of guess inference about the entire population. So I go out and I measure something just about a smaller group, and then from that I kind of guess what's going to happen about the whole group. And we'll get to how to do that more later this semester. So first off, you should be able to determine if something is a statistic or a parameter. Which one is it? So for the first example here, we have to, it says, according to the Census Bureau, the total number of housing units in the U.S. is 132,850,059. Now, because this is the Census Bureau and they're looking at the whole U.S., this would be a population value. We're looking at the entire country, so that's going to make it a parameter. Because again, parameters measure the whole, the entire population. And again, we use censuses to measure population. So that was a good hint that, yeah, this is a population value because we used a census to measure a parameter. So that's the whole population. So anytime you use a parameter, you're measuring the whole population, everything. Okay, the next thing says, a recent California health interview survey included 2,799 adolescent residents of California. Because they didn't include everybody in California, they just included just a part. This is just a part of California. So this is just a part. This makes this a sampling, right? So we're just sampling, not doing the whole thing. So then this data about this is going to give us a statistic. So this is going to be a statistic because it's just dealing with part statistic. So anytime you're only dealing with part of the group and not the whole thing, you're doing a statistic. Okay, last one. An instructor surveys a class to determine the average grade level of his students. So this one, we got to think about, again, what's the whole population versus what's the part. Now you can actually make this one, you can kind of play with this a little bit. So first off, if you think of just the one class as population, well then this would be a parameter because you measured the average grade level for that entire class. However, most professors usually have more than one class. We usually tend to teach a few at a time. So I'd say that this is probably not really a parameter. This is probably going to be a statistic. So we'll say statistic because we'll assume that he probably has more than one class. So he was looking at just a class. So that's probably part because his whole population in this case would be all of his classes. So a lot of times you kind of have to know the overall picture. What's the whole thing? So again, in this case, we'd have to know that his whole thing is all of his classes, or maybe all the classes he's taught of this type. You know, if it's the statistics class, it's all the statistics classes ever taught, or maybe all the statistics classes he's teaching the semester. That population would be more than just one class, and this would be a statistic. If he is just looking at one class, he decides that is his population, he's just working with just one class, that's his population, then it would be a parameter, because the class would be the whole thing. But again, like I said, most of the time, one class isn't going to be all the classes. It's going to just be one of its classes. And so this would be a statistic. You always want to clarify when you're doing questions about whether it's a parameter statistic, what is the whole? What is the entire population? And then do you have just part of it, or do you have all of it when you've actually gone out and measured all of it? So you should know the difference between a population and a sample. These are terms we'll come back to a lot this semester. We're going to do a lot with samples and sampling, and we're going to refer to populations as we go. So these are things that come back a lot. So again, population is the entire group. Sample is just a part. Okay, some types of data. So first off, we have two main types, or flavors, if you will, of data. Those two types are qualitative, also called categorical, or quantitative, also called numerical. So qualitative data is any kind of data that consists of names and labels. So these are things where you're going to label it, things like hair color, eye color, what state do you live in? Those are labels, names. You can have numbers for qualitative data, but only those numbers are being used as labels. So maybe you have swimming classes and they have 5 different levels. You can be in the first level, second level, third, fourth, fifth level of swimming classes. Those labels then are just, those numbers 1, 2, 3, 4, 5, they're just labels, labeling which swimming class. They're not actually defining as numbers, it's not counting how many people are in the class or anything. Then you could use it for qualitative. Typically qualitative, though, it's just going to be some kind of label. It's not even a number. It's going to be a lot of different things like what college you go to, what car do you drive, what kind of pet do you have. All those things would be labels. They wouldn't be numbers. Quantitative is going to be numerical. It's going to be numbers. So it's something you're going to get when you count or measure. So this is going to be numbers, and those numbers are going to come from counting or measuring. So things like how many pets do you have? How old is the car that you drive? So how many years old is it? Your height, weight, all that kind of stuff. That would be numerical data. That would be quantitative. So quantitative is numerical data. It's stuff you can go and you can count or you can measure. Now, quantitative numerical data breaks into 2 main groups. Those 2 main groups are discrete or continuous. So when you're working with discrete or continuous data, you're working with quantitative data because it's going to be the numbers in this sense. Now, discrete quantitative data is stuff that is finite or countable. What's that mean? Well, finite just means it's not infinite. That's why it's missing the part in from infinite. So it's something where it ends. Example would be like kids' shoe sizes. You start at size 1 and they go up to whatever it is, I don't know, like 12, 15, something like that, and then they stop because after that you're wearing adult shoes or young adult shoes. So kids' shoe sizes only go up so many sizes and then they stop. And so they're finite. There's only so many options for what size of shoe you can buy for a kid. Countable is going to be something like adult shoe sizes. You can always get a bigger and bigger and bigger shoe size, so they don't stop. There's no ending point, so they're not quite finite. In real life, yeah, they probably only go up so far, but theoretically, if you get a big enough person, you can always get a bigger shoe. But when you do the shoes, you can count them, right? Your size 1, or size 1, 2, 3, 4, 5, 10, 11, 12, so on and so forth. And so that's going to be countable. So stuff you can count through is going to be countable. And again, finite is going to end. So finite, it ends. And then countable, you can count it. That's a good way to think of it. So it's a set of things you can just count through. Sometimes you might have to count forever. That's why it's not finite. It's infinite. It can keep going. But you should be able to count the things. So discrete is going to have one of those 2 properties. It's either going to end. There's going to be a limited number of options, for the data, or countable, where it's going to have infinite options, but you're going to be able to sit there and count through the options. Now, the big difference, the other one, continuous. Continuous is something where you go and you can have something that's uncountable. Typically what this means for us is that uncountable means it's measurable. So instead of counting it, you're going to measure. That means that it's things like weight or height, where you can't count heights because there's all those options in between. Well, yeah, I could be 5'5", I could be 5'10", but there's all those options in between. Even between 5'10" and 5'11", there's options in there, right? Because you could be 5'10" and a half, or you could be 5'10" and 3/4. So this is going to be when you have measuring, because there's always options between 2 numbers when you measure. there's not just a list you can count. You just can't count all the heights because there's so many of them actually. So I call it uncountable because you can't just sit there and count through them. So that's what uncountable means. It's stuff we typically measure. So you have discrete quantitative data and continuous quantitative data. Discrete, and we call it discrete. It means that basically there's like kind of stair steps. Step from 1 to 2, 3, 4, 5. Nice little stair steps. Continuous, it just spreads through, and there's not nice steps. It's like walking up a ramp versus stair steps. You can kind of think of discrete as like stair steps, where every time you hit the next number, you're up, the next stair, versus continuous is like a ramp where you go up and down, and you're always getting a little bit taller, but you can't. It's hard to say exactly. There's all those values in between. There's not like discrete stops because it just goes up forever. So discrete could be like a stair step. Continuous could be like a ramp. Okay, so let's identify some data. First, we have to figure out if it's qualitative or quantitative. So we're going to know, is it qualitative or quantitative first. If it's qualitative, then we're done. We'll just have a label. If it's quantitative, again, quantitative, we have to say whether it's discrete or continuous. So we'll determine that after we figure out if it's quantitative. Okay, an elementary statistics course performs a study to determine how many pieces of color are in each bag of Skittles candy. So we look at the number of pieces. So how many pieces? Well, that is a number. This is definitely a number here, and we're counting this number. So this is a quantitative value. It's not just a label. The colors are labels, but we're counting how many of each piece. So this is going to be quantitative because we are sitting there and counting the different colors. Now, because it's quantitative, we have to decide, is it going to be discrete or continuous? Well, since we're counting the number, we're not measuring the size of Skittles. We're counting the Skittles. This is going to be discrete. Yeah, you could, if you have a big enough Skittles bag, you can always have more and more and more Skittles, so you have really big numbers, but it is something you can count. So we'll say that is discrete. So that Skittles counting makes it discrete. Okay, next one. The same class uses a digital scale to measure precisely the weight of Skittles in each bag of candy. Well, now since they're measuring the weight, it is still quantitative because we're looking at a number. The weight is going to be a number, so it's quantitative. It's not a number that's a label because it's actually the weight. It's actually a measurement. So quantitative. And because we're measuring that weight, this is going to be continuous. And there's always those decimal fraction betweens. It's going to be 1 gram. It could be 1.5 grams. It would be 1.25 grams. So it's continuous. So if you're measuring like this, that means it's going to be continuous when you're done with quantitative data. Okay, in a study of service times at McDonald's drive-up window, the number of cars serviced in an hour is recorded for several days. So again, they're looking at number, so this is a good sign. It's probably going to be quantitative. So we're thinking quantitative because we're counting the number of cars, right? So we're going to do the number. And then we're doing that number of cars serviced in an hour, and we'll record that for several days. So because it's number, again, we're thinking quantitative. And then we have to think, is this going to be discrete or continuous? Well, we're not measuring the cars like width or height or anything like that. We're actually counting how many cars there are. Since we're counting again, this is going to be discrete. That is discrete. Okay, got one more. Study of birth years of CEOs of America's 500 largest publicly traded corps. So this is birth years. We're looking at what year they were born. That is a number, but in this case, the number is actually being used as a label. It just labeled a specific year. It's not something we're counting. It's not something we're measuring. We're just saying, what year were they born? This is just a label. It's just a numerical label. So in this case, this is actually going to be qualitative because it's a measurement, but it's just a label. So qualitative. I don't know. When you're trying to spell words in front of people, that's when you make all the mistakes, right? Whoops. All right, so qualitative. Qualitative because the year is a label in this case. We're not counting the, not measuring. If you ask me, to collect data about the age of the CEOs, then that would be numbered because I'm measuring how long they've been alive. But since we're looking at their birth year, we're just looking at a label. So again, labels are qualitative. This isn't a numerical number. Even though we're using a number, we're just using a number as a label. That's the big difference between the two. Okay. Okay, beyond that, we actually have different levels of measurement. So different data sets you work with have different levels they can be measured, or different levels of measurement. First level we say is something that's nominal. So a data set that is nominal cannot be arranged in order, in numerical order. So there's no order to put this in. So this would be stuff like hair color or eye color. Those are not things we can order, right? How do you order hair color numerically or eye color? Those things are not things you can't do that. You can't arrange them. So they will be nominal. Next step up would be ordinal. So ordinal can be arranged in order, but differences are meaningless. So that's the big thing here is you can't put things in order. So you can put them in order, so you can't find the differences between them. It doesn't make any sense. So maybe an example would be the shoe size, right? We talked about shoe size earlier. So shoe size, you can order shoe size from smallest to biggest, right? But differences don't really make sense, right? Like size 10 minus size 9, what's the difference between those? Especially when you get to kind of maybe more labels that are even more abstract. So maybe instead of shoe size, if you think about like, I don't know, like sizes where you have something where it's like large, extra large, extra, extra large. Those really doesn't make sense to subtract. So something like that. Sizes where you can order it maybe by size, but you can't subtract. So maybe shoe size is the perfect example because you kind of think about like 10 minus 8, they're two sizes apart. So, but again, those are kind of arbitrary labels too. So, okay, interval is the next one. So interval can be ordered, has meaningful differences, so now it makes sense to subtract, but there's no obvious starting point. So no place really makes sense as a starting point. Example might be like birth year again. So if I go back to birth year, you can order birth years, right? So you can look at what year people are born. So the order makes sense. Differences, it makes sense. If someone was born in 1990 and someone else was born in 2000, there's 10 years difference. Difference makes sense. But there's no natural starting point. Where do you start? Maybe you might think 0, but remember the 0 is just, 2,000 years ago. There was lots of years before that, plenty of years before that. So 0 doesn't really make sense as a starting point. So it's like, where do you start? So there is no natural starting point for years, birth years. So that's a good example of something that can be ordered. Differences make sense, but there's no starting point. Okay, and then the last one, ratio. So data that's a ratio. Ratio can be ordered. There's differences that make sense, and it has a natural starting point. A good example of this would be like times. How long does it take this experiment to happen? I'm in science class, I'm doing an experiment. The length of time, you could order the times from the shortest time to the longest time. Difference makes sense. This time took 10 seconds longer than that time. So differences make sense. And then the natural starting point, well, natural starting point in that case is 0 time, right? You're not going to take less than 0 amount of time because 0 is the shortest amount of time. So maybe like experimental time. So something like that. Something where it makes sense. 0 is a good starting point most of the time, not with years, because again, we said 0 is kind of arbitrary. But like with time, 0 makes a lot of sense. All right, let's look at some examples and decide what they would fit in. So we have an exit poll is conducted in which voters are asked to identify their political party affiliation. Are they Democrat, Independent, Republican, so on and so forth. Doesn't really make sense to put this in numerical order. They're not numbers. You can't really order them in numbers. So it can't be ordered. And since it can't be ordered, it's actually going to fall in just that first set. So this is going to be nominal because it can't be ordered. Not numerically. So no numerical order. You could maybe order these alphabetically, but that's just arbitrary. Let's just do it alphabetically. So we don't have a numerical way to organize them. So they're definitely nominal. Okay, in a study of bank service times, the time it takes a customer to get help from a bank. So how long it takes an employee is measured starting from the time they enter the bank. Put a Y there. Whoops, a little typo in my notes. Okay, so the time it takes them to get service once they enter the bank. Well, you can order times, right? You just do the least to the greatest, so that makes sense. Differences make sense because when you subtract, it took 15 minutes for this guy and 10 minutes for that guy, 5-minute difference. Obvious starting point, when they first entered the bank, right? So it's times 0. So it does have an obviously starting point. So this would be a ratio. So it does have an obvious starting point, which is when they walked into the bank. Starting point of 0 time. So So because when they entered the bank, that's the time zero. That's an obvious starting point. So yeah, this is definitely a ratio. It has all the things. All right, next one. The average temperature is recorded over the year by a local news station. Makes sense. You can arrange it because you can arrange the different temperatures, from lowest to highest. Differences make sense. 10 degrees more, 10 degrees less. The differences make sense. Here we'd say there's no obvious starting point though, right? Because you can go below zero. You can have negative temperatures. So where's the bottom? Where's the starting point? Well, there isn't one. So in this case, this would be interval. We wouldn't use zero because you can go below zero. You could have an average temperature below zero. So we wouldn't want to start at zero because you miss out on all those below temperatures. So no obvious starting point. I know it's tempting to use zero, but it doesn't really make sense with temperature. Zero is just something we picked to be in the middle of the temperature ranges. So no obvious starting point. Okay. A magazine performs a study observing the shirt size of actors that have won an Oscar for best actor. Ooh, sorry. Shirt size. Okay, so we're looking at shirt size. Shirt size, you can arrange that in order, right? Small to large. Differences don't make sense, especially if you think of shirt sizes in like large, medium, extra small. So I'd say in this case, that's actually going to be ordinal. Ordinal. You can order from smallest to greatest. It's a kind of a numerical order going from least to most, smallest to greatest or greatest to least. So you can order, but differences don't make sense. The differences are meaningless. What is extra small minus a large? Like, what is that? It doesn't make sense. The differences don't make sense. So that would be ordinal. Okay, so we have those different ways of categorizing our data. So data has different levels of measurement. So when you're working with data, if you have data that's ratio, you can kind of do all the things. You can think about where the starting point is, you can think about the differences, you can order it, versus if you go all the way back down to nominal, it doesn't even make sense to put an order. So we'll have to work with those different types of data in different situations. It's good to know that they have different amounts of measurement you can apply. Okay, when you collect data, you collect it using different sampling methods. Again, remember we sample. When we have a sample, we're going to use sampling methods. We're going to use sampling to collect information about a part of the whole group. So we have, I think, 6 different sampling methods. Not all of these are great. Some of these are awful, but they're all used. There's people all over the place using all these different methods. And so we'll talk about which ones are kind of better, but these all happen. First one is called voluntary response. And this is anytime you do a sample where the respondents choose to be included. That means the person that's going to respond decides whether or not they're going to respond. So they volunteer to respond. These are not great. People don't really like to use these for real studies because having people choose to respond actually influences the survey. Who's going to respond? Well, people that feel strongly one way or the other typically are the ones going to respond. People are kind of more middle of the road are going to be left out. A lot of times you'll skew it to one opinion or the other because it's voluntary. Simple random sample is actually the best possible way of taking sampling. So this is a way of taking a sampling where when you sample, every sample of the same size has equal chances of selection. This is a little bit of a confusing definition. Basically, it means that if I go in there and I pick any group size, pick 5 members, and I say, okay, look at 5 people at one time. This tells me that any group of 5 people, so whether it's the first 5, the last 5, 5 randomly picked throughout the group, they all have the same chances of getting picked. That's what makes it simple random sample. So any possible group of 5 people has the same chances of getting picked. So you have to have so much randomness in this. All the groups have an equal chance of getting picked. Not just each person, but every group has to have an equal chance of getting picked. This is hard to do in real life. Simple random sample is hard to develop. It's hard to do, especially with really big populations. But if you can do it, it's the best possible one. A lot of times you'll see our homework later on the semester will actually say, hey, this sample is taken with a simple random sample because it usually makes the math easiest. And since we're just in intro to stats, we don't want really hard math yet. We'll save the harder math for the higher level stats courses. They can deal with the harder stuff. So we're going to stay most of the time that we took a simple random sample, even though that's hard to do because it makes our math a little bit easier because we have the best possible sample. Every sample of the same size, has equal chances. That's a simple random sample. Okay, systematic sampling. So, from the word systematic, this is following some kind of pattern. So what we do is we randomly select a starting point. That's how you start. So you pick somewhere to start randomly, random choice, and then the rest of the sample we select by pattern. So the rest of the sample, we actually follow some kind of pattern. You pick every 5th person, or every 10th person, or every 12th person, or you do every other person, but you're doing some kind of pattern. The first person picks randomly, and then the rest is picked following a pattern. Convenience sampling. So convenience is literally what that thinks. You should think of when you see the word convenience. You should think convenient. And that's what it is. It's what's easy. It's what's easy. That's all it is. So use data that is easy to obtain. That's convenience sampling. This is probably the worst type of sampling because you're not trying to pick a good sample at all. You're just trying to pick what's easy to pick. I'm just going to make an easy sample, call it good. So this happens a lot because a lot of times people are just being lazy and just want an easy sample, but it's a very bad way to pick samples. Stratified. So stratified, we take and we subdivide. So we break it into categories. Like if you're doing a study of the U.S., you might like the categories might be the different states. So people in South Dakota, North Dakota, Wyoming, all be different samples. They'd be different categories. And then in this case, you would actually just take a small sample of each. So like if someone's doing a study to kind of figure out what's going to happen with the next presidential election, what they might do is they might actually divide all the different states up and then pick small samples from each state and then use that to actually decide about the entire election. Instead of looking at the entire country at once, they kind of subdivide it. It makes your life a little bit easier. It's not quite as good as a simple random sample. Definitely better than convenience. But here you're breaking into categories and then sampling from a little bit from each category. So every category is going to be represented. Now cluster sampling is similar. We're still subdividing the categories, but now instead of picking just a piece of every category, we're going to select one or more categories. That's the big difference. So one or more categories is what makes this different. So now I'd pick like South Dakota and Wyoming. Those would be the two I picked, and then the rest of them I'm not going to look at. So you can see how that might have issues, right? If I look at the population of the U.S. and I just pick 2 random states, I might have a pretty skewed representation. Depending on what you're working at, some things that might not be such a big deal. The categories are a little more arbitrary or a little more mixed up. But again, this is going to be not as good as that simple random sample. Okay, let's identify some of these examples, what kind of method they're using. So first off, a student conducted a survey on driving habits by randomly selecting 3 different classes, surveying all of the students as they left those classes. So they picked randomly 3 different classes. Well, this is going to be cluster. So they subdivided, so the categories were the classes, and then they selected some of those classes. So this is going to be cluster as the method. Because they used categories and then picked some of those categories, then we're going to do cluster. So that's cluster. Okay, a local news station posts a poll on their website asking their viewers which candidates will win the upcoming mayoral election. So because they post a poll on their website and just let people fill it in who want to, this is very much a voluntary response. So people that care about the poll, care about this news station, they're going to respond. Anybody that doesn't really care about this poll or this news station, they're not going to be part of this, so they're not going to matter. So this is just going to be voluntary response. They didn't go out and ask people to fill it in. They just, here it is, and people that wanted to did. Okay. A student conducts a survey of sleeping habits by asking the first 20 classmates he runs into. So just the first 20 people he runs into. Very convenient, and it's definitely convenience sampling. He's just doing what's easy. That's all he's doing. Hey, what's easy? Okay, that's convenient. That's what I'll do. That's convenient sampling. Publisher studied the length of best-selling novels by separating the novels into categories. Oh, there's that word categories. So now we know we're doing stratified or cluster. Those have categories. So those are different categories. And taking a sample of each category. Now there's the word each again. So since he's looking at all the categories, a little bit from each, that's going to be a stratified sampling where you take a piece from each. So this is stratified. Sample just a little bit of each. Okay. 5. A college administrator studies the involvement level of students on campus by using a random number generator to select 15 students from a numbered list of all students. So he's using a nice random number generator, good randomness from a random number generator. He just picked 15 out of a big numbered list. So everybody, all 15 all groups of 15 students all have equal chances. So this is a simple random sample. This was easy to do because he had a list of all the students and he had a nice random number generator. But in real life, again, when you have really big populations like the whole US, this is kind of hard to do. In this case, because he had a small list, even if he has thousands of students, that's small compared to the billions of people on the planet or millions of people in the nation. So it's a small list, and you could just use a nice random number generator. So this is simple random sample. Every group of 15 students had equal chances of getting picked because of the way he did this. So that's a simple random sample. Okay, last one. High school principal surveys student opinions of a new lunch service staff by asking every 10th student leaving the cafeteria. So he's looking at every 10th student. That's a pattern. And when we see patterns like that, we should think be systematic. So systematic, you pick the first one at random. So he just randomly picked a student to start with, and then he follows a pattern. Well, now he's doing the every 10th pattern, so this is systematic. So again, all these sampling test methods happen in real life. There's reasons to do them because they make life easier or they might cost less, but a lot of times they're not really viable ways. If you went and looked at a professional study, statistical study, and they used convenience or voluntary sampling, you would just throw that study in the trash because then you know it's not worth anything. But a lot of times people do those kind of studies. If you look at news websites or stuff like that, they're doing voluntary studies all the time. Okay, we kind of talked about simple random sample. It's important to note that there is a difference between simple random samples and random samples. So a random sample is actually not quite good enough. That's not as good as a simple random sample. A random sample, every person has an equal chance of being picked. So if you look at any two people, they both have equal chances. But a simple random sample doesn't just have that for individuals, it also has it for groups. So every group has equal chances of being picked. So a simple random sample is actually more important because every group has equal chances, not just every individual. Groups of size 1, that's also a group, would also have equal chances. So it's still random, but it's more than random. So this is actually like harder, more important. So that's something we look for. We look for that. Does it have that simple randomness? And that's something we'll see throughout the rest of the semester. Okay, so let's look at examples to see if we can determine which one's which. So say all students' names are placed in a hat and 5 names are drawn. I don't know why I have a decimal there. Okay. So all students are put in a hat, 5 names are drawn. Well, every group of 5 students has an equal chance of being picked, right? Because when you pick your 5 names out of a hat, who knows which ones are going to be picked? They all have equal chances. So this is definitely simple random. Every group of 5 students has equal chances. An instructor randomly selects a row of 8 students to help with a project. Because he picks a row of 8, not a diagonal line of 8, not a cluster of 8, only the rows actually have equal chances of being picked. Every student has equal chances because there's only so many rows, and each student's in one of those rows. So they all have, like, I don't know, if there's 10 rows, they have 1/10 a chance of getting picked. So every student has equal chances, but every group of 8 does not, because some group of 8 can't be picked. A diagonal line of 8 students can't be picked. A cluster of 8 students all sitting up, rectangle together, that can't be picked. So this one is just random. It's not simple random, because some groups of 8 can't be chosen. Not with this method. So it's not simple random because there are some groups that just don't have a chance of getting picked. So that's not going to, be simple random. An athlete measures her heart rate for 4 times during the day with at least an hour between each measurement. Now, because she's spacing these out with that hour, that means that like 4 heart rates, like 5 minutes apart, can't all be measured. Every heart rate throughout the day has a chance of getting picked, just like the rest do. Because we don't know which one she's randomly starting with. But those, 4 heart rates that are right next to each other within like 5 minutes, they're not going to get all picked. That cluster's not going to get picked. So she's doing this 4 times a day, but she's spacing them out, so that makes this random and not simple random. She needs some kind of random number generator to tell her, when to do her heart check, and then she'd have simple random. You shuffle a deck of cards and you draw 6 cards from the deck. Now, because we shuffle this first, any set of 6 cards could end up on the top. So in this case, this actually is simple random. It feels weird because we're picking the top 6 cards, but because of the shuffling process, we're putting any possible group of 6 cards on the top. So every group of 6 cards has an equal chance of being the ones that get shuffled onto the top. So that makes it simple random because all groups of 6 cards have equal chance of being on the top and getting drawn. Last one, a manager has 100 plays. He lists at random on 10 sheets of paper, 10 per page, and then chooses a sheet at random. Well, because he put those sheets together first and then he chose a sheet at random, well, now he only has, he can only pick those that are groups of 10. You can't get like 1 from each page or 2 from each page. You can't do that to get 10. So because of making those sheets like that, this is actually going to be random, not simple random. Because after he clustered them into those groups, he made it so not all groups of 10 can have equal chances. So you can see how random and simple random are kind of similar, but they're different enough. It's important to know the difference. Again, simple random is a little bit harder to get. It's a little bit less likely. And it's where every group has equal chances. Drawing names out of a hat, cards out of a deck, that is simple random. So simple random is definitely possible, but it's harder to do. Okay, we're getting there. We think we've got 2 pages left. Okay, so when you do studies, when you go and collect data and stuff, you have 2 main ways of doing it. First is experiment. An experiment is where you actually apply some kind of treatment. You do something, and then you observe the effects. So treatment applied, the effects are observed. That's going to be an experiment. So if something happens, you make people do something, you give people something, you give them a medical dose, and you observe the results. Observational study. So an observational study is where you just observe or measure, without modification. So you're not changing things. So this is where you might just hand out a survey and say, hey, fill in these answers, and you didn't do anything to them, you just gave them a survey and asked them to fill it out. Or you might look at data that someone else already has, the census data, something, just collect information from that. So observation, you're not changing things, you're not influencing these with, to do an experiment. That's the big difference. Let's look and see if these things are experimental or observational. Sociologist has created a brief survey to be given to 2,000 adults randomly selected from the US. Again, he's not changing anything. He's not doing anything to them. They're just filling out a survey, so this would definitely be observational. He's not, performing an experiment on them. He's just gave them a survey and say, hey, fill this out, please. In a physician's health study, 22,071 male physicians were given aspirin or given a placebo. Well, they're given medicine. So this is an experiment now. He's changed what happened to them because he gave them the medicine. Okay, an independent researcher tested the effectiveness of the Atkins weight loss program by calling 1,000 selected subjects from the program. Now, because he didn't perform the weight loss program, he's just looking at people that participated and then calling them and asking them afterwards. This one actually would be observational. Now, if you're the person doing the Atkins study and you had people do different versions, or one group do it, one group not do it, then you would be doing an experiment. Because he's actually looking at people that already did it and just talking to them afterwards, his is very much an observational study. Okay. When you do studies, experiments, stuff like that, you have to be careful to make sure you have a good study. So some things you need to make a good experiment, so some things that are important for experimental design. One is replication. You should be able to repeat the experiment on more than one individual. So if you can only do it to one person, it's not a good study. Larger sample sizes are always the best. You should be able to repeat this, do it often, do it a lot more times, and get a larger sample. Single blind. Single blind is important. It means that the subject doesn't know whether or not they are getting the treatment. That's why people use placebos. I don't know if you know what a placebo is, but a placebo is just a sugar pill people get instead of the actual pill. So it looks like the pill, it smells like, maybe it doesn't smell like the pill, but it looks like the pill, colored and all that. But then when you take it, you're just taking a little pill of sugar. So it's not really going to have much of an influence on you because it's just sugar. So people do those placebos because then the patient doesn't know if they're one of the people getting the real medicine or one of the people just getting sugar. And then they can study what happens to people that really do get the medicine versus people that don't. They have shown in the past that if you give someone a pill and tell them they're getting the pill, and then someone doesn't get anything, the group that gets the pill even, will actually have better health results just because they think that they're getting medication that will help them. So that's why we use placebos now, because that kind of takes that out of the consideration. So subject doesn't know. That's a single blind. So they don't know if they're getting the pill or if they're getting the placebo. The double blind is when both the subject and the tester don't know. So again, they did studies and they actually found out that sometimes the tester knowing whether the person's getting the placebo or not, whether they're getting the medication or not, can actually affect the outcome as well. So it's important that both the subject and the person administering the drugs, the tester, both don't know. If they both don't know which one the person's getting, then they can't influence it. And so that's why we do know double-blind tests for drugs and stuff like that. Last thing, randomization. When you're doing an experiment, you need some form of randomization. So you're going to randomly pick which people are going to go to the control group. Control just means the group that get like the placebo or the sugar pill if they don't get the real treatment, or the treatment group. You don't want to pick this, systematically. You want to pick it randomly because that will help make your study a better study. Okay, last page here, on the last page of notes. Some things that happen when you take samples, there are forms of sampling error. So sampling error, there's mistakes or there's bad results from your data that can happen. First form is what we call sampling error specifically, and that is when you have good random techniques, you're using a good study method, you're actually going out and collecting random data, all that, you're not doing convenience or voluntary testing, but the sample that you randomly selected does not reflect the population just by random chance. This is the problem. When you pick a group of 10 people to study a group of 1,000 people, if you get unlucky, you just might pick the 10 people with the highest level or the lowest level. They're not a good representation. In that case, you've got a bad sample, and there's nothing you can do about it because you didn't know it. You just took a random sample. So the sample does not reflect, and it's due to random chance. No, you didn't do nothing wrong. You didn't make mistakes. You just got a bad sample. And that happens. That's why people do large samples. That's why people do multi-step tests, or you do test over again to see what happened, because sometimes it's just random chance. Non-sampling error, so this is not from the sampling, this is human-caused error. So this is things where humans make things messed up, make mistakes. You put wrong entries in, so when you're filling out your survey, just fill it out wrong. Someone writes biased questions that sway people one way or the other. People lie, false responses. That actually was what people thought was when they tried to predict the election 2 elections ago, presidential election. Everybody trying to predict it was really wrong on the predictions. I think one of the main reasons is people are giving false responses. They were saying they're going to vote for one candidate when they actually voted for the other, so that made it not work. They might not be using correct statistical methods. They might be using the wrong methods to collect their data. So these are human error. That's non-sampling error. And then non-random sampling error, that's when your sample is not random. So when you do things like the voluntary, convenience, systematic, so it's not random anymore. So if you do not random, then you're going to end up with some things affecting your group. If you do voluntary, again, like I said before, you have certain types of people respond. It's going to mess up your survey because it's not going to be very reflective of the entire group. Okay. Last thing to talk about, some potential pitfalls when you're collecting data or doing studies. First thing is to watch out for misleading conclusions. Just because you collected good data, got your information, doesn't mean you're always going to give the results that are actually meaningful or right. So when you collect your data, always make clear conclusions that are justified. The data should really support them. It's really easy to kind of mislead people with data. Measure sample data. So one thing people have found in the past is if you ask people what their weight is, they'll tell you one thing. If you go and you stick them on a scale, you'll get a different answer because people don't like to be honest about their weight. So don't ask the subject to report. Always measure yourself if you can. As much as you can, you should always go and actually measure the values yourself to get good, accurate data. Loaded questions. So this is that whole phrasing of your question. If you word your question badly, you can actually influence what the results are. So be careful about loaded questions. Phrasing can influence results. So be careful about the phrasing, how your questions are worded. The order of questions, so the order of the words within the question, or even the order of the questions in a survey, either way, can affect the results. So a lot of surveys, if they're done well and professionally, the questions in the survey will be randomized. So you won't see the same questions in the same order as the other person participating, because the order of wording, order of the questions can affect the results. So you've got to be careful of that if you're designing surveys. Non-response. If too many people don't respond, your survey is going to get skewed because it basically turns it into a voluntary response. The only people that did respond were the ones that decided to. So when people do surveys, they actually have to keep track how many people just didn't respond. And they might work harder to get those people to respond. Because if they get too low of a percentage of people that respond, then their survey is not valid. So non-response can be skewed by those who responded and those that did not. That difference. Okay, last thing, percentages. A lot of times studies will give out their information. They might look at percentages of groups. Be careful about percentages because percentages could be very misleading. So, watch out for percentages. If you see a study, a statistical study, and 80 percentages, A lot of times they can use that to be misleading. Okay, so like I said, this section, you will have a homework section on it. It's not really going to be covered on the exam, so you don't have to really worry about this for the exam. But these terms will keep coming back to a lot of these terms. We'll talk about populations, sampling, simple random samples, some of these different sampling techniques. This will come back later as we come into the rest of the section and do the rest of the work. And it's good to know these terms, but again, I won't test you over these. So, all right, thank you much for watching, and I'll see you on the next set of notes.